Recording? Yeah. All right. Thank you everyone for coming to our first seminar of the year. Today we have Professor Sinervo. I could of course list the many achievements in physics that he has and all the various accolades. However, today we're most interested in science communication. And Professor Sinervo is the professor for Physics 1600, which is the science communications course, graduate course in the department. So we've asked him today to come tell us about something related to science communication, and he will tell us about scientific writing.
Okay, thanks, Evan. So, thanks for the invitation. As you can imagine, given that I teach Physics 1600, I actually care, I guess, about scientific communication. I think last year you had a talk on scientific presentations by Joseph Sywithan. Not sure how many people actually tuned into that. That also came out of Physics 1600. He was teaching it last year. Come on in, join the club. So, we take, scientific communication has more than just the writing and giving presentations associated with it. In 1600, we also have what we call extemporaneous talks. People are given a list of 4 topics and they have 10 minutes to actually come up with a 5-minute talk. No slides, no notes, just come and actually talk. It takes a bit of training to do that, but if you think it is actually possible to do, and by the time the course is over, everybody actually has done 2 or 3 of them and they're all pros at it. So that's just another form of scientific communication. But we'll stick with writing today. So, writing is something that, we've actually all had some experience with. But what we also know is that very few people actually have a lot of experience with writing scientific pieces. By the way, your lab notebooks don't count as scientific writing, not really. And they get, if they've done writing, they get actually very modest amount of feedback. And as you probably know, if you don't get feedback on doing something, then it's actually hard to improve. So one of the things we've actually been working on, and I think in a lot of the undergraduate courses, we try now to actually introduce writing in a more instrumental way. Okay, so again, we actually all come from different backgrounds. English, for some of us, is a second language. It was a second language for me way back when I came from Finland. My first language was Finnish. We have not worried about grammar or style in your lab notebooks, which is probably where you've done most of your writing. People actually who do writing, they tend not to think that they can actually get better. And of course, that's not true. You can get better pretty much at anything, but writing in particular. And writing becomes actually increasingly essential, especially if you're talking about doing a graduate program. You are going to have to do some real writing. Writing is a thesis or a dissertation. You probably, for people who've been taking supervised research courses already, they've had to do writing. So it is actually going to be essential. And for people who actually think that now they don't have to write because ChatGPT or Copilot or Gemini are around, that's actually not the case. And we'll see a few examples of that. So it does take practice, right? It does take some time and attention to detail. And we'll talk a little bit about what kind of time it takes and how you should be using your time when you're actually writing. So there are actually a lot of resources that I actually recommend people actually go and consult. The one that's probably the most useful is Michael Alley's book, The Craft of Scientific Writing. It's not a particularly long book, But he actually goes through, and in fact, I'll be using a fair bit of the material or the way he presents writing in the presentation. He also writes a craft of scientific presentation, which you probably heard about last year from Joseph. And he actually is, from that, the scientific presentation point of the perspective is actually quite interesting because there's almost no research done on how effective scientific presentations are. You can have different ways of giving presentations, and some ways work better than others. Some ways don't work at all. And we actually don't get a lot of feedback when we actually give a presentation. I think usually what you do is you actually copy the style that you've actually been experiencing, which may or may not be a good example. Writing in some sense is similar. Though you actually have had more experience and at least more feedback over the course of the years. There are some other ones that are more sort of technical. Strunk and White, The Elements of Style. There's an APS style guide. Style guides are, for those who don't know, are in fact sort of manuals which say how you should write. They actually give details on what is appropriate punctuation, what are the appropriate choice of spellings of words, how do you actually write references, and each journal or the publisher has a different style guide. Newspapers have style guides. So Strunk and White is actually one that's used pretty commonly in the academy. And APS style guide is actually one that is actually a good reference for those who are doing writing in physics. For those who actually want to have fun, Lynn Struss's book, Eats, Shoots, and Leaves, is actually a fun little book that actually talks about punctuation. Have anyone read Eats, Shoots, and Leaves? So even the title actually tells you something about what it actually is, what's actually going on here. Is someone actually shooting something or is someone eating shoots? But okay. And then I'll talk a little bit about this last one, writing without bullshit, which is sort of an interesting topic in itself. So, my title talks about hallucinations, and we've all heard about the large language models hallucinating and doing funny things. If you actually go and start typing into Copilot and start asking scientific questions, actually a lot of the time you get things that look reasonable, which is actually not so unreasonable given that they actually scrape the stuff off of websites which actually have a fair bit of scientific work in them. But let me actually look at one. I asked Copilot, can we solve the hierarchy problem? Not sure how many people know what the hierarchy problem is. But it's basically, does anyone? Yeah, how would you, in one sentence?
It is the problem of current need for two parameters to cancel exactly these fractions like.
Yeah. So it's this problem that when you go to very high energies, much higher in the Planck scale, what happens is that for example, the Higgs boson mass is a number now, 125 GeV. But when you go to the Planck scale, 125 GeV is an extraordinarily small number. And you have to be able to predict the size of that number from going down from the Planck scale using basically quantum corrections, radiative corrections. So those radiative corrections have to be good to tens of decimal places. That's kind of it's improbable that could just happen naturally. So usually that's why we think there's some physics between here, our energy scale, and the Planck scale, because otherwise it's hard to see how you could get that kind of quantum correction. But so it's a big question. So what does Copilot tell us when I ask? It says no complete solution currently exists. The real problem with this is, what do you mean no complete solution? suggests that there's an incomplete solution or a partial solution. There is zero solution to the hierarchy problem, right? It is, a conceptual issue. There's not even an agreement that it's a problem. it's just part of the standard model, right? Okay, so and you can actually then it actually gives you a list of sort of things that actually talk about, the what are maybe possible sort of comments about it, and it's extraordinarily incomplete, a little bit wrong in places. This emergent paradigms garbage, it has this list of things. Well, okay, you know, it can look, if you're not an expert, it can look very reasonable, right? But it's all hallucination. Okay. And of course, then, would you like a summary comparing all major proposed solutions? All major proposed solutions. Give me a break. I looked at that. And, I teach a course in Beyond Standard Model Physics, and we talk about the hierarchy problem. And what ChatGPT tells me is nothing I would actually present in that course. But okay, just a word of warning. But we'll talk about that a little bit more in detail. So when we talk about writing, you can actually step back a little bit from scientific writing itself. But there are sort of ways of breaking down what are the key elements of it. And when we're talking about scientific writing, probably the most important criterion that you're trying to meet is that it be precise. A lot, when we actually think about writing in a journal, one of the reasons we're writing in a journal or writing a piece for a journal is that it allows people to first know what you've observed and also know how you've observed it, so that someone actually can go and reproduce what you've actually done. And as we know, reproduction is the core as a scientific enterprise. You can't reproduce the result. Something's wrong. Either the prescription you have is wrong, or the original observation is wrong. But that's the way science self-corrects. So it's important for any scientific piece to be precise. Okay, but precision also requires clarity. What you write has to be clear to the people who are writing it. It can't obfuscate the issue. But then there are ways that you can actually achieve that. One is when you're writing, just be forthright. We'll talk a little bit about what that really means, but forthright means that you're just going to say what you've done. Just don't beat around the bush. Don't try to try to hide the issues. Just say, just state the facts. But also be clear. Then there are sort of aspects of writing which make writing easier and more effective. One is being concise. Okay? You can take a word out of something you've written and it doesn't change the meaning, take it out. In this context, the way you can think about it is that you're writing something and that takes a lot of time. But your time is less important than the time of all the readers. So if you're throwing in a lot of unnecessary words or sentences or paragraphs, you're wasting everybody else's time. It also doesn't make it any clearer. It actually makes it harder to actually understand what really matters in the piece and what doesn't. So when I write something, for example, my first draft, I will probably pull out something like a quarter of the words or sentences. And I've been writing for a long time. And when I'm writing, it's a bit of a stream of consciousness. And then when I go back, I begin to realize I really don't need to say that, or I've already said it, or I'm using extra words that I don't need. So we'll talk a little bit more about that process. And then this idea of writing in a fluid way, in a familiar way. Fluid, it's a bit hard to define precisely, but you know when it's not fluid. Perhaps more, not fluid means that when you're writing, sentences don't hang together, paragraphs don't hang together. It's actually jarring. It's hard to understand because there isn't kind of a very clear stream of of argument or thought or explanation. And And being familiar is even more, it's imprecise in some sense. Being familiar means that you're writing in a way that people actually don't feel as pretentious, that you actually are not writing down to somebody, but you're actually talking to them. You're communicating in a way that you're trying to make as effective as possible. Okay? So, these are sorts of things that one should be clear, but all of these things end up actually helping it be what you're writing be clear, and most importantly, that it's precise. Hi, come on in and join the club. Okay. So now, hi, come on in. Okay, so there are what we would call 3 organizational issues that you should actually keep in mind first before you actually even start writing. There are constraints on what you need to take into account, and you might as well know them before you actually start putting fingers to keyboards or pen to paper. There is a question of structure of what you're writing. How should it be structured? Sometimes you have some choices. Often you have constraints and things that you actually don't have any real choice in. And then there's questions of style. The different journals or different contexts, you actually need to know what the style is and adhere to it. Either at the beginning or at the end, but you're going to end up having to adhere to it. So let's actually talk about the constraints first. So there are 4 that you can identify right off the top that are constraints in what you write. And often we don't think about these, but it's really important to be conscious of them. The first is audience. Who are you writing for? A very different piece that you're going to write if it's for the PhysRev letters or it's an op-ed piece in the Globe and Mail. Very, very different audiences. And you need to know that right up front. Are you writing to a very specialized audience that kind of knows all the jargon? You have you can use it if you know it's very familiar and everyone understands that vocabulary. Often that's not the case. And so you have to be conscious of exactly who's going to be reading it, which then determines how you would actually write, what sort of vocabulary you would write. Format is another constraint. You can think of it just as the fact that when you actually look at different books or journals, they actually have different ways of laying out text on pages. Sometimes it's double column. If it's a long equation, PhysRev letters cuts it across several columns. There's a lot of things which are very specific to the given journal or the context in which you're writing. So you need to know that because that does in fact inform and may actually change the way you present things. The third is what was put in the category of mechanics. What are, for example, the styles that you have to follow? Now, are you using British spelling or American spelling? Are you actually using particular choices of the commas? There's a Harvard comma. There's a Chicago comma. There are these very specific issues which actually will come up, and they're all captured in this context called style. And it's not always logical, but you have to know. You have to know. And finally, there is a thing that most people don't really think about explicitly, and it's the politics of what you're writing. If you're writing a piece that is actually about global warming and the physics or science of global warming, you would write a very different piece if you knew that the audience was largely skeptical or scientifically literate and actually already bought into the idea of global warming or the global climate change. If you actually, if you have a skeptical audience and you assume that everyone's going to believe you, and they've already bought in, they're going to stop reading. They're not going to read it. So if you want people to actually understand what you're saying and communicate with them, you have to know what are the barriers, potential barriers there are, and don't piss off the audience right from the start. You can actually get your message through, even if it's an audience which may be skeptical or hostile to your message, as long as you understand how you actually are able to present things in a manner that doesn't turn the audience off. So it's, it's something that you should keep in mind. Sometimes we don't really worry about it too much, but there are other cases, especially if you're writing to a broader audience, it really does matter. Okay, so structure. So here I'm going to talk about something that's very, specific, and this now really comes back to writing the reports or scientific articles, on results. And so the typical structure you have, well, we all have titles. You can't get away from that. Abstract or executive summaries are often the case, usually an abstract. Sometimes if you're writing a report, you'll see an executive summary. Talk a little bit about what that means. There are main sections, pretty obvious what that is. Illustrations, tables, there's a conclusion, and there may be things at the end, back matter, the additional, the materials. Many journals now actually allow that. It didn't used to be the case 20 years ago, but they now allow a fair bit of additional material. And I was talking with the senior editor of PhysRev Letters, who actually came and gave a colloquium here about 4 weeks ago, thereabouts. And we were talking about the fact that PhysRev Letters used to have a very strict page limit of 4 journal pages. And the reason for that was that they wanted to use every piece of white space in the journal. And so if you limited everyone to 4 pages, you knew they were going to write right up to the end of the 4th page, because they really wanted to say more, but they actually were going to be constrained. And so now you had a journal that was chock full. You didn't have any blank pages. You didn't have half pages. It was, it was a way of minimizing paper cost and printing cost. Well, today it doesn't matter. It's not on paper any longer. In fact, there are very few copies of PhysRev Letters actually on paper format. Very expensive to produce. And a small number of them are produced, but I'm not sure who in the audience has actually read a PhysRev letter out of the journal on paper. Right? Okay. The sort of premier journal in physics. And you never see it in paper form. So the page limit has relaxed in PhysRev Letters, even though they still format it in pages. It's now more than 4. Okay, well, back matter now is also allowed in PhysRev Letters. They never would have allowed that before. And you can have any number of quite a few pages of additional information. Okay, so let's talk about title first. When you actually think about a piece of, a journal article you're writing, how many people look at what we call the archive? ARXIV. Right, okay. So it is actually the repository that almost everyone in the field uses as a way of keeping up with the literature. It's not published, not peer-reviewed, but it's actually there right away. And so if you're actually looking for new results, you typically are scanning it for things that are interesting. But it's a fire hose of material every day. Even in your own specialized areas, there's a lot of stuff that comes out every day. Some of it really, really good and important. And a lot of it either mediocre or just crap. So you have to find a way of actually being pretty efficient at figuring out what's actually worthwhile even looking at. So the first thing you do is look at the title. And if the title doesn't actually communicate and capture you, you're going to go on. That's, you're not even going to look at the abstract. So the title matters. You're not trying to get everyone to read your paper, but you really want everyone who you want to read the paper, right? So the title should actually be able to achieve that. So here are a bunch of different titles. Reducing the hazards of operation, interaction-free measurements, studies on the electrodeposition of lead on copper, use of an IR50, observation of a new particle in the search for the standard model Higgs boson with the Atlas detector at the LHC. Okay, so which of these are good and which of these are bad? What's your favorite or worst one? Yeah.
The first one looks pretty bad.
Yeah, okay.
Unclear what this is about.
Right. Operations, what hazards, right? It's almost content free, right?
Yeah.
But you can also see here, okay, use of an IR FPA in determining the temperature of a grating. Well, IR, I get. FPA? I even forget what FPA stands for. At one point I knew, but okay. And so, if you actually go down and analyze these things, so, okay, what operation? People already made that point. Okay, what measurement? Interaction-free measurements. You can just go down the list. This looks pretty good, but of an object in a light beam, right? That we're talking about a molecule. We're talking about the a small ball. What is it that we're actually talking about? This isn't great because studies could be anything. And if you're actually going to, again, this could have been, okay, what are you really studying? And just say it. Just put it in the title. Right, IRFPA. So in fact, some journals will not allow you to put abbreviations into the title. Just this last week, we had an argument with the journal editor because we were writing a paper on the dark matter search, and the type of detector we've actually been using is one that we've developed and used for the last close to 20 years, and what we call an HVEV detector. High voltage electron volt detector. It actually can measure single electron energies. Okay, so very well known in the literature. The editor complained about the fact that we're trying to put an abbreviation into the title. They relented after we pushed back, but nonetheless, you actually still get that. And then this last one, this was actually the title of the paper that actually reported the discovery of the Higgs boson by Atlas. And it's no longer 5,000, it's actually more like 15, but okay. And there was a similar paper that had a very similar title coming from the other collaboration, CMS, on the same day. But, it's a very long title, right? But it's pretty descriptive. And there are some constraints in politics. You needed to say LHC in the title, right? The Large Hadron Collider. You needed to have the collaboration in the title. And this was the observation of new particle. It didn't say it was the observation of a Higgs boson, because at that point we didn't have enough evidence to claim that we actually had observed the Higgs boson. But we could claim that we were looking for it and we found something, right? Okay. And, in about a year's time, we were able to say that we had discovered the Higgs boson because it had all the properties of the Higgs boson. So if it quacks like a duck and it waddles like a duck, it's probably a duck. Right? Okay. So abstracts. I mentioned that there are two different forms of sort of summaries or abstracts in an article. The first, which is the one that is probably most common, is one that just tells the reader what the article is about. Okay. It's short, The PRL limit, for example, is 600 characters. And if you think about what 600 characters is, an average word is around 6 to 8 characters. Okay, so you have something like between 80 and 100 words in the abstract. So, if you think about how many sentences, how many words in a sentence, so you have 5 or 6 sentences. Okay. Then there is this, what we call an informative or executive summary. And it summarizes the key findings and often the recommendations, typically about a page. So sometimes, for example, the Council of Canadian Academies writes these very detailed reports commissioned by the federal government, typically. And they have an executive summary, which is typically 7 or 8 pages long. The report itself may be 150 or 200 pages. But that executive summary is something that people could read and capture most of the, at least, outcomes from the study. So I'm going to actually look at one particular paper as an example through this talk, because it actually exemplifies a lot of the issues. Here was the abstract for a paper that actually became quite important because it actually measured the top quark mass. How many people know what the top quark is? Sort of. There are 6 quarks. Top quark is the heaviest of the quarks, but the weight of a gold atom. And when it was discovered, one of the big, its mass is actually one of those parameters that you really need to know as precisely as possible. Okay, so this was a measurement, okay, using the CDF detector at the Fermilab Tevatron, and it came up with a particular measurement of the top quark mass using one technique, and then a third, or a second, and then it actually just used the most precise value. But the importance of this paper was not just the value of the mass, but what it actually introduced was a technique for constraining the largest source of uncertainty in the measurement, what we would call the energy scale calibration of jets in the event. That was a thing which had limited all of the measurements of the top quark mass up to that point. And at that point, it had been measured for about 10 years. And what it introduced was a way of actually constraining that uncertainty in a manner that as you collected more data, it would actually fall naturally. So we all of a sudden eliminated a limitation that had been there for 10 years. Okay, and this was actually published about 20 years ago, and it's still the most precise technique. Okay, all right. So that's why I'm using it as an example in some sense. Okay, so let's talk now about some of the other elements of the paper. We've talked about title, we've talked about abstract. So now you have sort of, think of a paper as having 3 sections. And it is a story, right? There's an introduction to it, then there's a body, and then there's the conclusions. And the introduction and conclusions really need to tie in. You're introducing a topic, you're introducing why you're making a measurement. And at the end, you should be saying, okay, what was the measurement? Why is it important? What have you learned? And in the middle is all of the text and the information that is intended to convince the reader or inform the reader what you've done and what the results are. So, introduction, what is the work? Why is it important? What is the context? How is it going to be presented to you? What is often there is sort of a bit of a roadmap for the paper in the introduction, quite common. The main section and the subsections describe what's done. There's usually a strategy for a measurement. You should make that very clear and then walk through how the strategy is implemented. It often has subsections to help navigate the topics as you go through, so that the subsections actually talk about specific information, steps in the process, and make it easier to read and keep track of what's going on. And then conclusions. First, you restate what was done. It's basically saying what you promised in the introduction. You summarize the key conclusions. And often people will talk a little bit about what the implications are for what might happen in the future. One has to be a little careful about that because sometimes the implications aren't going to actually be realized. Rutherford's paper in 1909 that actually reported the discovery of the nucleus. Remember the experiment? What did Rutherford do? Yeah, the gold foil. And what was he actually pushing through the foil? Yeah, alpha radiation. Right, okay. So the paper, it's a great paper. People should go and read it. You can find it online. I actually, at the time I first read it, I had to go over to the SIGSAM, the Science and Medicine Library, that was called, and go down 4 floors into the archives where we actually had the Royal Society proceedings. Can now do it in about 5 seconds online. But in the back of the paper, he says, and we're going to then provide additional information about how the behavior of the nucleus is. Never wrote it. Okay. So, it's an example where, the world's leading scientist actually goes and makes a promise at the back of the paper and doesn't deliver. Right? So, be a little cautious. If you're going to make promises, then you should actually be prepared or already in the process of producing it. Okay, so the PRL article of the abstract you just saw earlier, this is the introduction. And I'm not going to have you want to read through all of it, but it first says what is the top quark? Why is it important? Within the context of Standard Model, the top quark is related to the masses of the W boson and the Higgs boson, and the latter object being the key to our understanding of the origins of mass. So we're trying to actually position the top quark and its mass in the context of why it's important in the context of the Standard Model. So an improved measurement of the top quark mass is therefore a main goal of the experiments. Okay. So it lays out why this should be actually important. And the introduction, and often the introductory paragraph, is at least as important as the abstract. When we actually talked about perusing the archive, right, the first thing you do is look at the title. If the title looks interesting, then you look at the abstract. Read the abstract and decide whether, in fact, it's worthwhile going further. The next step is you read the introduction, if the abstract has got you going. And often then you'll go and read the conclusions. And it's only after you've done that would you then decide whether you're going to invest the time into reading the rest of the paper. Does that sound about right? Yeah. So what it tells you is the introduction is important, abstract probably the most important, conclusions are important if you want the paper to be read. We all would like everyone to read our papers, right? But okay. So anyway, so this is actually was the attempt to grab the reader. So anyone interested in top quarks would probably read this paper, given what was actually said in the introduction. Okay, in this paper, it's a PhysRev letter. It consisted of 17 paragraphs, 3 figures, and 2 tables. When you have, if you look at PRL, you find that they never have more than about 4 figures, because each figure takes away a paragraph of text. So with the balance, you find that you have to be very parsimonious. But okay, so this is a kind of this is actually from the journal page. And you'll notice that the comment I'd make is that here's what we call a displayed equation. I see them all the time. But one thing is to note that it's numbered. And some people will say, I should just number equations that are the most important in the paper. The fallacy with that is that you don't know what's actually going to be most important 10 years from now when someone reads the paper. one of the reasons for actually numbering equations is that someone can refer to them. So in some other subsequent paper, someone can say, in journal blah, 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 equation blah actually shows the what the relationships are, or equation blah is wrong. Take your pick. But having the equation numbered allows you to do that. If you decide ahead of time which equations matter and which don't, okay, you make referencing at least those elements in the paper very difficult. So it's good practice just to number everything. So the second comment I'd make is that this is one entire paragraph here. A lengthy paragraph like that is not great. And the reason it's not great is that, when people actually read something, what do you do at the end of a paragraph? You just ignore it? What does it suggest to you when you get to the end of a paragraph? An idea. That paragraph is supposed to somehow convey an idea. Now, when you get to the end of it first, now the writer is telling you, okay, the idea, this is the idea. But secondly, most people will actually, if they're going to try to understand the paper, they will stop at the end of the paragraph and try to make sure they have actually captured everything up to that point. So it's very much part of the cognitive process by which you absorb information in the paper. So the end of a paragraph is really quite strategic. So how you choose paragraphs matters. If you put more than one idea into a paragraph, someone reading it will actually have to then parse all that, keep track of it until they come to the end. They're not going to typically stop in the middle. First, you don't know where you stopped. If you actually start thinking where's at the end of a paragraph, you know. So paragraphs serve a very specific, very functional purpose. So a long paragraph is not great. Now, we actually spent a lot of time trying to think about how we broke up that paragraph. But that paragraph was all about getting down to this equation. So we had to describe each of the elements in this equation in order to make it meaningful. So that was actually what we ended up sort of compromising on. And if you would, I would argue that if you read this, you actually begin to appreciate that, this is a likelihood, and we needed to describe all the components of it, because this is actually the statistical tool used to extract the measurement. Okay. The other sort of interesting comment here is that this caption of a figure is actually quite long. One of the problems with captions of figures and tables is that they are usually the last thing you think about. You say, I'm going to have a figure, I'm going to have a table, that's great, you're going to embed them, and then you actually have to say something about them, describe them. And often, it's already a bit too late to do that because you've already written the text that the table or figure is going to reference. And some of the information, the key information in the figure now is embedded in the text. It's very hard if someone just looks at the figure to understand what's actually being presented, if they then have to read some part of the text where it's actually referenced. So the figure caption should actually provide enough information that someone reading the caption will understand what's in the figure, understand all the elements of it. They don't have to somehow find that information buried in the text. So sometimes figure captions are short because that information is very clear. And sometimes they have to be fairly long. And in this case, there were 3 distributions shown here, plus this inset. So kind of needed some description. And there are even some things here like, well, the last bin includes an overflow, namely that when you're doing histograms, often if you cut something off, there are some data beyond where you cut it off. You make the last bin count the number of events you've actually not included. Okay, well, you need to say that somewhere. So that usually needs to be put into the caption. Okay, and then finally, there are actually statements here that we could have actually removed, just taken out of the paragraph. You read it in the following way. So we don't need to say in the following way. We would just simply say it. It's not a very smooth way of actually talking about it, but it's somewhat colloquial. You could actually do this exercise throughout the paper. But that kind of exercise had been done several times already because this paper, when it first was written, was way too long for a PRL. Okay. So conclusions, they have to be given a lot of thought as to how you're going to conclude and what you're going to say in the conclusion. So here, again, it basically repeats what was actually already expounded and presented in the main body. And in this case, there were two measurements of the same quantity using a data sample that was strongly correlated. So instead of attempting to understand what the correlation is and put the two measurements together into one simply took the most precise one as the measurement you're going to quote. And just treat the second one as just an auxiliary measurement that just reinforces the idea that you've done the right thing. Okay, and this provides the most precise single constraint on this parameter exceeding the accuracy of the previous world average. Okay. So again, it's attempting to put the measurement into context. Okay, let's see what Copilot does. The Copilot, in order to actually get to anything that looks like that result or to actually be able to report that result, here are all the prompts I had to give it. First, describe how we most accurately measure the top quark mass. Well, it didn't get anywhere there. It gave me a list of all of the most recent measurements, but not how. Okay, what are the limiting factors? Well, this was attempting to get it to spit out that the jet energy scale was a limiting factor. But it didn't quite get that far. I then had to actually go and then talk about the jet energy scale. And so, okay, so this prompt gave me, and then it asked, give me an essay, and have the essay focus on the first measurements in 2005. I had to be really precise. I had to tell Copilot what it was looking for. All right. Then it produced this essay. It was, I'm not going to go through it, but this is what it produced. It was a LaTeX file. It even gave a few figures. This piece of garbage here as a figure. Okay, missing key references was rather, salutary. Oh, this was great, blah, blah, blah. It was somewhat, they did some plagiarism, missed some key details. Okay. Most importantly, when it actually summarized all the measurements, it got this one completely wrong by an order of magnitude. This number is not 3.7 GeV. It's actually the 640.64 GeV. Okay, only a factor of 5, not an order of magnitude. Okay, but this is, if you looked at this, you'd say, okay, that was actually what was actually going on. And I know why it did this. It actually claimed this was a Tevatron average. It missed the fact that there was an average measurement that was done 5 years later. Just missed it. Okay. So what really pissed me off was that there was an archival piece that explained this jet energy scale constraint business that we wrote back in 1990. And Copilot said, well, this came out of a collaboration called the Solenoidal Detector Collaboration for the SSC. We had written a lot of papers. Copilot said it found all the SDC papers and there wasn't anything there that talked about this. And of course there was. Okay. Tells you about the dangers, if you like, of using anything having to do with a large language model to do science. Okay, so there are a lot of things that, that one can actually go back and look at these criteria I started with. Clarity, avoid complexity, keep it simple, stupid. Avoid ambiguity, concision, omit unnecessary words, precision, use the correct word. Use the incorrect word or something that's just a sort of an approximation to it. That's not helpful. Avoid excessive use of synonyms. Don't use the same thing, don't call it different names in the paper. Stick to a single set of terminology for it to avoid any confusion. Familiarity, avoid jargon. Remember who your audience is that you're writing to. You should be writing in a way that's familiar to them. Forthright, avoid pretentious words or cliches. They don't help at all. Use concrete nouns rather than abstract nouns. And a concrete noun, the oscilloscope, an abstract noun it's an instrument, right? Okay, avoid passive verbs. What's a good choice of a passive verb? The measurement was made by is a passive verb. We made the measurement. That's an active verb. And actually passive voice versus active voice. Be suspicious of any sentences starting with it. Okay, because if it starts with it, then the first question is, well, what does it refer to? At the beginning of the sentence. Is it something that ended the previous sentence? Was it the subject of the previous sentence? It actually always creates ambiguity. So be suspicious. Be specific rather than general. Try to be as specific as possible. For fluidity, just vary the rhythm when you're writing. It's not a situation where we did this and we did that and we observed this and we observed that, but actually talk about we made this measurement. After having made this measurement, we found that that discovery led us to blah blah. You're actually changing the way you're actually the sentence structure, and it makes it easier to read. And it doesn't get you bored. Okay, writing without bullshit. Okay, so this is a great book. Everyone should probably go and read it. It's really intended for us scientists and technical folks. And he makes Burnoff as an author, he actually makes the case that more and more written material is being generated. And this is a thank you to the World Wide Web. It's more and more unedited. There's less discipline in it. And he invokes as what he calls an iron imperative. I already mentioned it. Treat the reader's time as more valuable than your own. Okay, so he has a measure of bullshit writing. And so this is actually the way he looks at it. This is actually taken from a website. In Avalon is a leading technology company that combines advanced cloud-based data analytics and data-driven intervention platforms to achieve meaningful insight and impact in clinical and quality outcome utilization and financial performance across the healthcare landscape. Okay. Right. What does it say? What does it say? Okay, so he actually goes and he says, okay, look for everything which is actually a meaningless or a content-free word. And these are the ones that he actually goes and highlights in the bold. Then he says, okay, take all the meaningful words, divide by the total number of words. And in this case, it's about 60% of the words are meaningful. Okay, the other 40% are bullshit. That's his sort of argument. And so, this is something that we all are probably, guilty of. Writing stuff which sounds really nice, but doesn't really have a lot of content. A bit being, we like to be a little bit pretentious. Most people, if you're a physicist, I suspect you've already started to get this sort of reaction. No, you must be very smart if you're taking physics. Okay. Well, that's actually probably true at some level. But all right. The point, though, is that we actually sometimes actually get a little bit, big for our britches. We actually can be a little bit more pretentious. My children tell me that all the time. Okay, so this is being precise. It's critical for effective communication. Email is the absolutely worst way of communicating stuff, unless you're prepared to spend a lot of time writing email, because it is actually a piece of writing, and it should be treated in exactly the same way as everything I've just talked about. Okay, so I'm not going to spend a lot of time. This was a question that was sent to, 3,000 collaboration member. I have a question on analyses strongly dependent on charm jets and light quark jet uncertainty. Should not include them when profiling. Okay, so I don't know how you define strongly dependent on, and why does the here he says should not include them when profiling. Okay, this is a statistical statement, but there was some question about why one should actually not do the profiling. And the rejoinder was actually about strongly dependent. It should just mean that a variation would significantly affect the analysis result. This went to 3,000 people, this exchange. And it was so detailed and so technical, and it wasn't all that clear to begin with. So just an example of the sort of things that you actually run into. Okay, so there are a bunch of things that are kind of redundant phrases that you should avoid. Alternative choices. Choices are alternatives, right? The consensus of opinion. Well, an opinion is a consensus. For the foreseeable future. What's the unforeseeable future? You sort of just go through these, right? For all intents and purposes, as opposed to all intents and purposes. But you have, those are, there are these wordy phrases as to whether a great deal of. There are a lot of things you can just get rid of, right? Just try to avoid them. And then finally, there is this agreement that active voice is more effective in communicating. And there are two categories. There's this passive verb and passive phrases, and first or second person. It used to be that you never wrote a scientific article in first person. We never did anything. Things got done. You removed the person, right, from the description of what happened. It was completely, kind of like it was a fiction. Of course people were there. Of course people did the measurement, right? But it was very much simply not allowed. Journals would not allow you to write in first person. They do now, but for a long time they did not. Passive verbs and passive phrases. So this is an example of passive versus active. Voltage was displayed on the oscilloscope. The oscilloscope displayed the voltage. Just, be straightforward. Just say what happened. Don't actually try to be passive about it. And first or second person, the measurement was done by analyzing data. We made the measurement by analyzing the data. Okay. And there are some caveats about not using first person too much, but that's really a matter of taste. And there's a bunch of random notes, which I don't have time to go through, but basically they give you some hints as to what actually the strategies for writing. For example, write the abstract last is not a bad strategy. Don't begin with it. And finally, when you actually write, this is typical, right? You start your thesis, 2 years later, all of a sudden you have number of words, all of a sudden it all comes up at the last, right? Not very uncommon. But a rough rule of thumb is to plan to use 25% of your time, so 25% of this 2 years to write the first draft, and the other 75% to make it better, to polish it. It really does require you to plan and give yourself that time. And it's about your time, and it's not wall clock time, right? How much time if you have a week to write something, well, get the first draft done in the first 2 days, and then the rest of that time you actually work to polish it and make it as good as possible. Okay, so so this comes back to the Jorge's other cartoon. You think carefully about each word before typing it. That's what you would like to be doing, and you keep pressing random buttons. Yeah, but okay, because we're actually always in a rush. Okay, so you all can become better at writers. I continue to try to get better as a writer because I know there are things that I do sort of innately that just are not necessarily the best possible. I continue to have to remind myself when I'm polishing and reading, why did I write that paragraph that way? I could have, it just was wrong. So it requires self-reflection and it requires a time. Okay, so that's thank you for all listening, and hopefully this helps.
One or two questions?
Yeah.
On that last section, when you go back and look in retrospect, maybe like a month, maybe like years past,
Yeah.
do you have a way to reduce the feeling of, oh wait, I should have done this way, I should have done this that way?
There's at some point you start feeling like you're writing stuff you've already written. It, I certainly developed some strategies for how to write better right from the start. I do try to put myself into a situation where I try to be as concise as possible. That's probably the thing I've done the most work on, just trying to be as concise as possible right from the beginning. It's easier to add stuff, I find, than it is to take it away. Now, some people find it's easier to edit yourself than it is to actually choose to add material. But my own style of writing, it's easier if I actually try to be as concise as possible to begin with. And then I can actually go back and look to see if I should be adding more detail. Doesn't always work that way. I still find that I write too much, but that's the thing I keep most conscious in the front of mind, because I know I'm just too verbose often. Yeah, Stephanie.
The first one is when I write reports. I know there's a large overlap of content and abstract summarizing this key point. And then I often find myself just like, which one, if I write the abstract first, my conclusion of that part of it is just like a paraphrase of that.
Right.
Is that how it works? Or do you have any advice?
Yeah. Yeah, that's actually, it is about how it should work. The abstract should actually get to the end, to the conclusion. If you have a measurement, it's actually good to have it in the abstract, because that's what people will look at. If they say, oh, that's an interesting measurement, then they'll actually go and look at the rest of it. So yes. You had a second one.
Yeah, my second question is, do you have any advice on writing collaboratively?
lot of ways of doing it. Doing something in the cloud is actually helpful, where you can, whether it's a Google Doc, right? Or whether you're doing LaTeX. That works pretty well. You have to have people who are conscious of how others feel about writing, someone writing at the same time you're writing. My own experience is that it's easier to decide how you're going to divide it up and let each person write their own sections, and then you figure out how you actually merge them and get them into the same style, as opposed to having people writing on top of each other. But using those sorts of tools, it's helpful. Google Docs, I find, actually works quite well. We're writing pieces, or 4 or 5 of us writing something, and someone makes a first draft, and then just waits and watches other people tear it apart or make improvements. And then you sort of go back and you sort of try to make sense of what's happened. But it has to be somewhat sequential. It can't be completely in parallel unless you divide and conquer.
So let's thank Professor Sinervo once again.
You're welcome. Thank you. That's nice.